And then tomorrow we will look at part 3. This is on page 31. And there are 2 examples we're going to look at today. Both of these examples still have a lower degree in the numerator than the denominator. And maybe just make a mental note. When you do have a lower degree in the numerator, you are dealing with partial fractions. When you do not, you're not dealing with partial fractions. You're going to do something different, which we'll learn tomorrow. First thing we want to do is rewrite this integrand as a sum of partial fractions. But I had mentioned yesterday, and we talked about this yesterday, but we didn't do one like this, that if there are 3 linear factors, you must have 3 partial fractions. And there are 3 linear factors. 2 just happen to be the same. So we're going to have a over x plus 2 plus b over x plus 3. Anybody remember what I told you the third one would be? Jay? X plus 3 quantity squared. That's right. And now we have to clear all of those denominators so that we can get an equation that will allow us to determine a, b, and c. And they're going to be cleared by multiplying. You can decide how you want to cram this in. I'm going to cram it in by doing this. And that's my way of telling you that I'm going to multiply each term on the left and the right by that common denominator. So what happens on the left, of course, is those denominators cancel in their entirety. We don't have anything left in the denominator. All we have is x squared plus x minus 4. So not only do they cancel in the denominator, none of the factors are left over in the numerator. Whereas in the first partial fraction on the left, on the right, the x plus 2 cancels, and I'm left with this. In the second one, the x plus 3, one of the x plus 3's cancel, and I'm left with x plus 2 times x plus 3. And in the final partial fraction, the only thing you're left with is the x plus 2. See if I got that right. A times x plus 3 squared looks fine. B times x plus 2 times x plus 3 is fine. And then C times x plus 2. And when you look at this, we're trying to find A, B, and C. It looks like a complicated thing, right? There's x's everywhere. There's A's, B's, and C's. Let's do the simple way out first by putting in strategically a value of x that eliminates 2 of those 3 terms on the right. Well, there's an x plus 2 in 2 of the terms. So if I were to use x equals negative 2, what would that produce? Well, it would produce 0 in this term and 0 in this term. So the only thing we would be left with is negative 2 squared plus negative 2 minus 4 is equal to a times negative 2 plus 3 quantity squared. You know, I don't think you really need to write this down, but these 2 terms are both 0 because negative 2 is a 0 of the factor included in those terms. There's an x plus 2 there. That works out to our advantage because on the right-hand side, all we have is a. A is equal to, I believe, negative 2. We're okay with that? So we have a down. Now what we can do is we can strategically place a different value of x in. And we're going to put in negative 3 because that will eliminate the a term and the c term and allow us to find the b term. So what is that going to give us? Let's see. It's going to give us negative 3 squared plus negative 3 minus 4 equals, the first term will be 0, the last term will be 0, the middle term will be b times negative 3 plus 2 times negative, pardon me, the middle term is gone as well. It's the last term that sticks around, isn't it? So this is 0. I mean, you discover that as quickly as I did because I was going to put negative 3 in here. Plus c, which is multiplied by negative 3 plus 2. That gives us negative c is equal to, I believe, 2, but I would want and appreciate your help there, 2. So a is negative 2, c is 2. Good? Right. How do you eliminate now the other ones so that you end up with something that you can use to find b? The answer is you don't. Using this method, now that you know what c is, you can load c up here. You know that a is negative 2. You can put that in. To find b, you pick any other number you want. Any other number you want. Because presumably, when we say that this original integrand is the same as the sum of these three fractions, presumably we're not saying, well, they're the same only with particular values of x. We're saying they're the same. So you should be able to use any value of x you want. What do you want to use? I might be tempted to use x equals 0 because it makes many of the calculations simpler. So, for example, when I put 0 into the left-hand side, and I'm looking here right now, everybody, I get negative 4 on the left. Let me just double check that. A is negative 2. I'm putting in 0 for x. 0 plus 3 is 3. Squared is 9 times negative 2 is negative 18. While I'm up here, I'm putting 0 in for x. So this will end up being 6 times b, which we don't know, I believe. So you're going to have plus 6b. And then plus, what are we going to have for c? c is multiplied by x plus 2. I'm using x equals 0. So 0 plus 2 is 2 times c, which was I don't know if I actually wrote that down. We got negative c equals 2. So c is also negative 2, correct? Okay. So I'm taking 0 plus 2, which is 2, times negative 2, which is negative 4. And now you can solve this for b. Negative 18 and negative 4 is negative 22. I add the 22 to the other side and get 18 equals 6b, which means, I'll write that down for you to see it, b is equal to 3. So now we know a, b, and c. That means the integrand that was is now a over x plus 2 plus b over x plus 3 plus c over x plus 3 squared. Is that the order that I had put them in for a, b, and c? A was negative 2. B was negative 2. No. B was 3. And C was negative 2. Is that correct? Okay. It's now just a matter of integrating that. Again, I think the hard work is getting there, finding out what A, B, and C are. This will be negative 2 ln x plus 2 plus 3 ln x plus 3. I want to say plus 2 over x plus 3. And that's just what went on in my head. I'm going to explain to you what I did. I'm thinking of the integral of negative 2 x plus 3 to the negative 2. So this is what I'm integrating. I put the negative outside. and I brought that x plus 3 squared to the top. So I increased the exponent by 1. I have to make kind of a correction here. No, I don't. That's good. That'll do it. That will give me a negative 2 times x plus 3 raised to the negative 2, which is what I want, plus your constant. Good? Okay. If you are interested in this kind of thing, then the proper kind of hoi polloi fancy way of doing it would be to expand all this out. And you would end up with an ax squared, you would end up with a bx squared from this and from this. You would end up with 6ax in here. You would end up with 5bx in here, and you have cx here. You would end up with 9a plus 5b plus 6b rather, plus 2c, and I want to double check all of those. 6x, so that's 6ax, 5x, that's 5bx, I have a cx, I have a 2c, 6b, 9a, it's good. So the idea is that if this is equal to 1x squared plus 1x minus 4, that this is equal to 1x squared. This is equal to 1x. And this is equal to negative 4. Your system of equations would be a plus b equals 1, because the sum of these coefficients has to give you 1x squared. 6a plus 5b plus c has to give you 1 as well, because the coefficient of x is 1, the sum of those coefficients has to be 1. And then 9a plus 6b plus 2c has to equal negative 4. So a plus b is the coefficient of x squared. 6a plus 5b plus c is the coefficient of x, and then the negative 4 is the sum of the constants. When I first did linear algebra and I had to solve a system of equation like this, this is a bit of work. And if you think of just putting in those strategic numbers for x, it's less work. If you are interested, you can certainly that's not a bad equation to start off with on the top row. You could certainly give that a crack. I don't think you're gaining anything by using your calculator here, because why don't you just put in the numbers for x? But you can certainly give that a crack. Take the middle row and subtract 6 at the top. You always want to try to subtract, because then you're still keeping integers. You don't have fractions. Take the bottom row and subtract 9 of the top. Then these two will be zeros. Then you can take whatever number you have here and subtract that number. Well, there's different ways to go here. I might change this to a 0 first, but it's up to you. But from there, you could get to reduced row echelon form with a bit of fortitude. Any questions with that example? All right, let's try one more, and this is where things get a little bit different. What's different about this one is that one of the factors in the denominator is a quadratic, which is what we call irreducible. I don't know why they don't just say non-factorable, but we say irreducible. You cannot factor it. And that means that this 8x squared plus 10x plus 37 over the product of these factors is going to be equal to the sum of a fraction of x minus 1 and a fraction of x squared plus 2x minus 8. I'm contemplating if I should explain why, and I'm not going to right now. I'm just going to say that I had mentioned this yesterday, that when you have your partial fractions, whatever the denominator is, the numerator is a constant because the denominator is linear. What that implies is, since the denominator of our second fraction is quadratic, the numerator is linear. The numerator must be 1 less than the denominator. You can, if you want, you can play around and see what would happen if you think this is going to work. And it won't work. Okay, it's not going to work. So we need to put bx plus c here. It goes beyond what we were talking about before. Now the general rule is you're going to have 3 parameters because the degree on the bottom is 3. It isn't that there's 3 factors. The degree is 3. So what are we going to have to do? We are going to have to multiply the numerator and denominator of this by, no, I keep saying that. We're going to have to multiply the left and the right side of this equation by the product of the denominators of the partial fractions, or if you like, by the denominator of the original integrand. And what we get on the left is the original numerator over here. The x minus 1 cancels and we're left with a times x squared plus 2x minus 8 plus 8. And then over here, what we end up with is bx plus c multiplied by the x minus 1, which doesn't cancel. I hope you can see that our cheating strategy doesn't work here. And it's kind of why I've said, well, we can use the cheating strategy, but here's the proper way to do it. Because sometimes you're going to need to use a system of equations. We need to expand this all out. Now, I'm perfectly aware that many of you can see that it's going to be ax squared plus bx squared for the x squareds. But this foiling is awkward. So let's FOIL it out piece by piece and see what we get. We end up with, for the first term on the right, the following 3 terms. A times x squared, 2x times a, 8 times a. Plus, man, this is a bit of a mess, bx squared minus bx is my outer, inner is cx, and then minus c, and I want to just double check that. That came out of my head a little too fast. Ax squared plus 2ax plus 8a plus, first is bx squared, outer is negative bx, inner is cx, last is negative c. That looks good. So this is equal to 8x squared plus 10x plus 37. These 2 terms have to give us 8x squared. Right? What does that mean about the coefficients of a and b? A plus b has to give you 8. And this isn't going to be a bad system of equations to solve because one of the equations already is missing a variable. or a parameter. What else do we have? We have 2ax and negative bx and cx. So these are all of my linear terms. That means that 2a minus b plus c has to equal 10 because we need it to have 10x. 2a times x, negative b times x, and c times x. What else do we know? We have 8a minus c is equal to 37. A plus b, I'll just double check these, is 8. 2a minus b plus c is equal to the coefficient of x. And the constants are 8a minus c. So how do we go about solving this? Well, there's lots of things we could do. One of the things I see is that if I add the bottom two equations, I have a single equation with a and b in it. And I also have an equation here with a and b. This top equation, compared to the sum of these two, is that. And you know, they don't always work out in our favor, but this is very convenient. This is how you would solve a system of equations with three variables. You'd use two of the equations to create an equation with only two of the variables. You'd use another pair of the three to find another equation with two of those variables, and then you'd solve that. Fortune shone on us today in that if we add these, the b's go away, and I'm left with 11a is equal to 55, which means now we know a is 5, and that cracks the case wide open, right? 55 divided by 11 is 5, because now we can put 5 in for a in the top equation and find b. Now that we know b and a, you can use whatever equation you want to find c. So a plus b is equal to 8, I think. Yep. Well, we just figured out that a is 5, which means b is 3. You know, 8a minus c is 37, so 8 times 5 minus c is 37. Well, 8 times 5 is 40. 40 minus 3 will give you 37, so c is 3. So what does that tell us? Like, this is, by the way, you can get so caught up in what we're doing here that go, okay, I'm done. I found a, b, and c. You're not done, because we did this so that we could rewrite that integral from the integral of whatever that was. I'm not going to rewrite it. Of a over, was it over x minus 1? And a we discovered is 5, plus bx plus c over, keep going.
Plus 2x plus 8.
So, we need to integrate 5 over x minus 1, which is easy. And we need to integrate this, which is easy but not as easy. This will be 5 times the natural logarithm of x minus 1. What do you suppose we can, or I don't know, need? I think we need to do something here. We can't use partial fractions because the bottom's not factorable. So all you would be doing is saying that this thing is equal to ax plus b over x squared plus 2x plus 8, and you would just be chasing your tail. You're climbing the wrong ladder there. You're not going anywhere. The ladder is just laying on the ground, actually. So partial fractions doesn't work. Will parts work? That's where you would choose something as u. I mean, it might, actually. I don't think I want to go there, but... just to remind you visually, that's kind of what I'm talking about with parts. I think you're asking for trouble, I think, if you do that. I don't even know that you'd be able to complete this. Well, you would, as long as you chose over here 1 over x squared plus 2x plus 8. But then this would get so unwieldy that your integral would be a problem. Will substitution work? Is there a piece, notice I say piece, is there a piece of this that's an argument of a bigger operation whose derivative contains another piece? Well, yeah, u, if we choose u, is x squared plus 2x plus 8, du is 2x plus 2 dx. And that, in a way, is in this integral. I can take a 3 out of the integrand. And there's a couple of ways to proceed here. I'm a little intellectually curious about something right now. How many of you, where's my dx? Would this thought potentially occur to you? That I have x plus 1 dx, but I want 2x plus 2 dx. So how many of you, don't necessarily write this. I wouldn't do this. How many of you would do this? I mean, that would work, right? It's the same thing. I would prefer instead that a student does this. So the x plus 1 dx will be 1/2 du. And this becomes now, sorry, I'm just exhausted today, becomes 3. That x plus 1 dx is 1/2 du. And this is 1 over u. Because the x squared plus 2x plus 8 is u. So we get 5 ln x minus 1 plus 3/2. You could probably do this next bit of business all in one shot. It's your call. I'm just going to move that 2 out first. Now I can integrate 1 over u du. And then, of course, you don't leave it there. You put in what u is equal to. U is equal to that x squared plus 2x plus 8. So my final answer here is that original integrand as a function of x is equal to 5 ln x minus 1 plus 3/2 ln x squared plus 2x plus 8 plus your constant if you don't want to get burned for half a mark. Okay. Does that make sense to you? Again, I'm very, very tired today, so I'm having a hard time sensing how well you're understanding this. I've got here for problem set at A, 9 and 11, and for B, 9 and 11. I would say you could do anything in those now, in A and B.